When the switch is turned on, the light turns on. It seems simple, right? However, the power supply is a used AA battery, which only has around 1.2 volts, not nearly enough to power the white LED, which needs 3 volts. Let's break this circuit down. This is the breadboard prototype of the Joule Thief or Vampire Torch. There's a used battery, a 1K ohm resistor, a white LED, a slide switch, an NPN transistor. But what about this component? This is known as a toroid coil, and it consists of an iron ferrite ring with two wires wrapped around it 5 times each. Now this works because when a wire has current flowing through it, it produces a magnetic field around it, and if you wrap this into a coil, this magnetic field becomes much more concentrated. Before we can talk about how this can be applied to the circuit, let's talk about transistors. A transistor is a semiconductor device that acts as an electronic switch. It has three terminals: the collector, the base, and the emitter. In this circuit, an NPN transistor is used, which means that without a base current, the transistor remains off and no current flows from the collector to the emitter. By default, the transistor blocks current. However, when a small current is applied to the base, it allows a much larger current to flow through the circuit from the collector to the emitter. Now let's look at the two important laws of the circuit, first being Faraday's law. This is where the concept of magnetic fields comes in. Faraday's law states that a change in magnetic flux will induce voltage, also known as an electric motive force or EMF. When the primary coil's current changes because of the transistor, it generates an EMF that is transferred to the nearby secondary coil, which is known as mutual induction. The second law is Lenz's law, which states that any induced current will oppose the change that caused it. For example, when a magnet, such as a compass, moves through a coil, it creates a current that generates a magnetic field, opposing the magnet's motion. This is why you can see the LED turns on as the system resists the change in the magnetic field. Now let's put that all together in this Fallstad simulator schematic. When the circuit is turned on, a small current flows into the base of the transistor, which turns it on just slightly. This allows current to flow through the primary coil, which creates a magnetic field. As it changes, it induces a voltage into the second coil, which is Faraday's law, feeding back into the base and turns on the transistor even more. This creates a positive feedback loop as the voltage keeps going up and the transistor switches on quickly. However, the magnetic field reaches its maximum and it will stop changing. The induced voltage disappears, the base current drops, and the transistor turns off. When that happens, Lenz's law will occur and the magnetic field collapses and produces a high voltage spike because it tries to oppose the change. This spike powers on the LED and the process repeats so quickly that the human eye cannot even see it.